So you should be able to see a PowerPoint screen. As Para mentioned, my name is Mark Mattingly Scott. That's a British name, but I've been living in Germany for the last 30 years. I'm working for IBM for the last 30 years. Prior to that, I was born and raised in Britain, educated in Britain, and worked for a number of years in research in another company in the UK. And I came over to Germany in November 1989, which was when the Berlin Wall fell, but it was also when the World Wide Web was launched. And my first job at IBM was looking at and understanding the World Wide Web. So it's a little bit of background to me. If you want to connect with me on LinkedIn, just scan the QR code and send me an invite. So the topic today is quantum computing. And just to start on this, I wanted to go a little bit into the background, the motivation for quantum computing. The picture you see here is of the current, actually, I think it's the second largest one we have, second largest quantum computer we have. And I'll talk a bit later about what all that stuff is and why it looks like that. But it all started around 40 years ago, in 1981, at a very, in the meantime, a very famous conference which took place at MIT, at Endicott House at MIT in Massachusetts. And this photograph is a very historic photograph for quantum computing, because at this conference, basically the idea of quantum computing was born. And if you look at the people in this photograph, if you Google May 1981 quantum computing photo, you'll find you'll probably almost certainly find this photograph. You'll probably find it with all the names in there. So I'm not going to ask the usual question, which is, can you identify any of the people? Because you guys have already done that. But interesting, in the second row, so standing up at the back, it's the 1, 2, 3, 4, 5, 6, 7, 8, 9th from the right. There's a guy with a very, very receding hairline standing at the very back. And this is Richard Feynman. And if you have anything to do with physics, particularly modern physics, then you will have at least heard his name. He's not as famous as Einstein or Heisenberg or Schrödinger, but he's up there among the greats. And Feynman had a Nobel Prize in physics, along with, I guess, about half the people in this photograph were also physicists. If you look at the front row of the people sitting down, the 7th from the right is a grey-haired old guy. That's Konrad Zuse, the father of the first electronic computer. The front row of the very left is Freeman Dyson, sat down on the very left. But the whole group is basically computer scientists and physicists of world renown back in 1981. At that time, I was still doing my Bachelor's of Science in Computer Science and in Applied Physics and Electronics. So, of course, I wasn't yet doing my PhD, so I wasn't aware of all this. But I do remember a few years later, when I was doing my PhD, I think it was 1984, an announcement that IBM had implemented or constructed a qubit with a coherence time in I think 50 femtoseconds or something like that. And the significance of that will become clear a little bit later on. So this conference basically was organized because, despite significant advances in the power of computers, So at this time was client-server was happening. Silicon chips were really starting to get a lot of transistors on them. The whole computer industry was geared up to grow massively. And then these physicists came along and they said, it sucks. It's not enough. We can't even do basic, simple kindergarten stuff with these computers. You need to do better. So this conference was basically organized to examine why that was and what could be done. And as it turned out, there's a fundamental problem in using classical computers to model the physical world. And Richard Feynman, so this is the guy on the back on the right, he said probably in order to model physical systems, and I mean basically since after the Second World War, the interesting stuff in physics has been either quantum physics or cosmology, so either the very small or the very large. And in chemistry, it's pretty well all quantum chemistry, so quantum mechanics. And Feynman said, probably in order to model these quantum mechanical systems, we're going to have to build a computer based on the same quantum mechanical systems. And that's a really, really interesting problem, how to do that. So that Feynman said this. I don't know if you can see the reference. I'll put it down here. So if any of you are online, then you can Google the International Journal of Theoretical Physics, volume 21, and you should be able to download a PDF for free. It's actually very, very well written. Feynman was a brilliant educator and very good at communicating. So have a read of that paper. If you read and understand that paper, then you're probably going to understand the basics of what motivated quantum computing. Now, in parallel, in 1970, an IBM fellow called Charlie Bennett started, he was doing his PhD, or may have been postdoc work, with Steve Wiesner. And these two guys came up with the idea of using the Einstein-Rosen-Podolsky experiment as a way to communicate. So they basically, in 1970, they invented quantum information theory. So IBM at that time in the 70s was working on quantum communication, so entangling qubits to be able to communicate. And at the conference, the physics conference, of course, IBM had this background in quantum information science, and then the physicists came along and said, we need quantum computers. And IBM looked at these two things and said, well, we put that together with that, maybe we could build a quantum computer. And that's exactly what happened. So the birth of quantum computing was basically in May 1981. If we look at the timeline of what's happened since 1981, obviously that's a few years have gone by since then, some very significant events are illustrated here on this foil. I guess the one that maybe people have heard of is in 1994, Peter Shor, who was a professor at, also at MIT, came up with an algorithm for factoring large numbers. Now, in cryptography, factoring large numbers is the basis of pretty well all public key cryptography because it's computationally difficult. In fact, I don't know the exact figure, but I think in order to factor a 1024-bit number using the largest computer on Earth, you'd need, somebody worked out you'd need 17 billion years. It's longer than the life of the universe. Peter Shor came up with an algorithm which theoretically would do that in about 10 minutes. And that's the difference between classical quantum computing. It's a massive speed up for particular problems. Now, I said theoretically because you don't need to worry anytime soon. Practically, we're not going to be able to crack 1024-bit RSA keys anytime in the near future. There are other reasons for that. So Peter Shor came up with this incredible speed-up algorithm for factoring large numbers. And in the 90s and the 2000s, there was a lot of work on developing new algorithms, new ways to solve problems, but also significant improvement and significant developments on the underlying technology, in other words, ways to implement qubits. And the big breakthrough came in 2010, 11, 12, where we really started to see what we call the coherence time of the quantum computer increase drastically through the use of superconducting Josephson junctions. And we then moved the technology from an area, from a space where coherence times were in the order of nanoseconds into microseconds. Currently, the best machine we have is a coherence time of over 100 microseconds. That means you have 100 microseconds in which to execute your quantum program, and that's quite a lot of time at the speeds we're working at. So in 2016, we made a variety of quantum computers available in the cloud, and I'll talk about that in a second. Just for comparison, this is the Oak Ridge National Laboratory Summit supercomputer. Some of the facts about this, it's pretty mind-boggling. So 4,608 nodes, and each node has 2 Power 9 processors with, I think, 12 cores, or 24 cores, 6 NVIDIA GPUs, and 2/3 of a terabyte of main memory. So the thing is huge. And it's the biggest supercomputer on Earth, and it can simulate a 46-qubit machine. And what that means, we'll talk about that in a second. So what was the challenge, not for the physicists, but for the computer manufacturers and computer scientists? So the physicists said, we have a problem and we need a different kind of computer to solve it. The computer manufacturers had a totally different problem. Now, I don't know if anybody's heard of this, but there is something called Moore's Law. It's named after a guy called Gordon Moore, who founded a silicon manufacturing company in the early 60s, Fairchild Corporation. So the first real bijunction transistor was in the late 50s, and Gordon Moore came along and started this company Fairchild, and they developed multi-transistor chips, incredible things. We now know them as integrated circuits. He developed the very first integrated circuits, actually for among other things, for the Apollo space program. And interestingly, one of the very first integrated circuit chips went up on Apollo 11 and landed on the moon. And in '64, Gordon Moore made an observation about manufacturing silicon. He saw that the size of the silicon die, the piece of silicon with a chip on it, the maximum manufacturable size of this die, where you can get a reasonable yield, was increasing every year. And in parallel, the size of the transistors you could put on that die was decreasing every year. And he put these two factors together and came up with something called Moore's Law, which originally stated that the number of transistors on a chip will double every 2 years. Looking back toward the 60s, we now know that that was a bit too conservative. It doubles about every 18 months. However, we're now at a phase where the largest single feasible silicon chip to get a reasonable yield is a couple of centimeters on the side, and the transistor gate size is of the order of 10 to 20 nanometers for a reasonable yield, which limits the chip to a few billion transistors. And that's basically getting to a bottleneck. So a lot of those transistors are being used to just communicate with other transistors. A transistor with that gate size at, I don't know, 20 nanometers has maybe 30 or 40 silicon atoms in it. So it no longer behaves like a good switch, like an on switch. It behaves like something which, on a good day, looks a little bit like a switch. So it's very error prone. So the current chips are limited in their ability to execute, basically, communicate and execute. And we're kind of reaching the limit of Moore's Law. To contrast that with quantum computing, the classical computer, in order to double the compute power, you need to double the effective and available number of transistors. Double that. With a quantum computer, to double the power of a quantum computer, you just need to add one single qubit. It's not trivial. It's trivial to manufacture, but it's not trivial to manage the error rates and performance and behavior. But basically, quantum computers scale in a totally different exponential way. So when we look at the history, the overall history of quantum computing, the foundations began in the 1800s, really up to 1930 with the developments in quantum physics with Schrödinger, Heisenberg, Einstein, Pauli, von Neumann, all these great names in physics started quantum physics as a discipline. From the 70s and 80s, we started to develop quantum computing, and basically from about 2016, when IBM put the very first quantum computers up on the cloud, we're talking about an era we call quantum readiness. So the idea and capabilities are that people, including all of you attending here, can use a quantum computer and experiment with it, can understand how quantum computing works, how it's different from classical computing for a programmer. And our customers can begin to actually examine how quantum computers might be used for real problems. At some point in the hopefully not too distant future, we will reach something we call quantum advantage. And quantum advantage is it's a kind of, the idea is a point in the future where the power of a quantum computer overtakes the most powerful computer available for that problem. And that will happen in different application areas at different times. So we're expecting to see that initially in areas around chemistry and pharmaceuticals, maybe agriculture, but also in planning, logistics, finance, and also in areas like machine learning and AI. So having said a little bit about quantum computing, let's look at the basics. So we recognize there are different types of quantum computing, but at the moment we have access to and use something called a NISQ computer, and a near-term intermediate quantum computer. So qubits have errors, they're error-prone. You don't have very many of them, but it's something you can start to use, experiment, and start to develop algorithms. There are a number of companies on the market offering something they also call quantum computing, which is actually a kind of variant called quantum annealing, which is a very specific use of low-temperature transistors. It isn't actually quantum computing because you don't get the two essential facets of quantum computing, the essential power of quantum computing. And at some point in the probably distant future, we will have something called universal fault-tolerant quantum computers, but that's still a long way away yet. Quick look at the machine. What does it look like? Let's move this over here. So basically, the quantum computer, this is not just IBM's quantum computer, this is pretty well, not all, but most of the quantum computers are also our competitors. It's operating at a very low temperature using helium-3 and helium-4 in a diffusion refrigerator to get the temperature down below the temperature in intergalactic space. So the temperature, the business end of the quantum computer, it's between 10 and 15 thousandths of a degree above absolute zero. And down in there, there's a superconducting, bunch of superconducting transistors, Josephson junctions, and we can beam microwaves at these Josephson junctions and put them into superposition and manipulate them and do things with those qubits. And all the plumbing and gold and copper wires you see there, all basically, it's basically wires. That's all it is. It's wires going in and wires going out. there's a whole bunch of control electronics. This is all working at microwave frequencies. There's a whole bunch of control electronics controlling that, manipulating it. The picture on the left shows that. Nowadays we're down to much smaller because obviously we're putting these things into something like production. So why are quantum computers so powerful? There are two principles here at work. The first is the principle of superposition, and I guess this is if you've heard about quantum computing, this is probably the thing you're familiar with. Superposition says that in contrast to a classical bit, which takes either the value 1 or 0 at any time, a qubit can take any value. It's actually any complex value imaginable with unit modulus. Sounds a little bit strange, but basically what that says is that the quantum computer, you can manipulate the value of a qubit in two different ways, two different phases, as long as it's in superposition. The second principle is the one we call entanglement. Actually, if you understand the really deep physics behind this, these two are two sides of the same coin. However, entanglement is the really strange part. It says that you can take two qubits, make them into one quantum system, and then if you separate them, for example, they still behave as one quantum system. So this is the principle that Charlie Bennett came up with back in the 70s, using entanglement to communicate. There are a lot of projects in Europe, increasing number of projects on using quantum entanglement for secure communication. But we can also use this in quantum computing. So we have these two principles, superposition and entanglement, and with those we can obviously define a qubit which takes on, as long as we don't observe it, and that's the key point. You're not allowed to observe these qubits. So you can initialize them, you can manipulate them, and as long as you don't look, they behave as a highly complex, high-dimensional quantum system. And the trick with doing quantum computing is to develop circuits, to develop experiments, programs, which do that initialization and manipulation. So you prepare, and then at the very, very end you observe, and what you observe is a result which has a particular meaning or a particular interpretation and delivers you the answer to the question you initially asked. So what does that look like? Well, let's go now to share my browser. So can you see this?
Yes, we can.
Okay, good. So this is the entry screen of IBM's quantum experience. So if you go on the internet and just IBM quantum experience, you will end up here. Okay. Now you can sign in. There we go. So I was already signed in, so I can't show you the login screen. But if you have a Google ID a LinkedIn ID, a GitHub ID, a Stack Exchange ID. There's a whole bunch of single sign-on methods we support here. This will give you access to the IBM Quantum Experience, where you can do, where you have access to a whole load of tutorials, but you can also use what we call the Circuit Composer or Python notebooks to access the real quantum computers. And what does that look like? Well, let's see. Before I talked about these the qubits and the fact that you can manipulate those qubits, so you can initialize them, you can apply rotations in phase space to them, you can combine them, and you can measure them. And when we do these operations, these low-level primitive operations on qubits, we are constructing what we call a quantum circuit. And the quantum composer is an application, GUI application for doing exactly that. So without further ado, let's take an H-gate. Now, you may be wondering, what's an H-gate? H stands for Hadamard. Hadamard is was a mathematician working in information theory. And the Hadamard transformation takes a qubit which has been initialized and puts that qubit into superposition. And what that means is that it's now its value is simultaneously a 0 and a 1 and every other possible value in between. If we then observe that qubit and repeat that experiment maybe 100 times, then it should be that 50 times it's a 0 and 50 times it's a 1. So let's try that, let's see if it works. So what you're seeing here is qubit 0, we're applying a Hadamard transform, and then this little element here is actually says, please observe it and give me the result. Okay. So we have to say the let's run it. Now you can see here a whole bunch of different icons. These are all what we call fundamental gates. And what you can do is here go onto the gates overview, do a description of what these various gates do. We can also look at how to use the composer. Let's just see what's happening here. Pending results. So I'm going to So we're going to come back to this in a few minutes. What we also offer, or what you can also do, some of you may be registered on Stack Exchange or use Stack Exchange. So the official support for IBM's Quantum Experience is on Stack Exchange. But if you're using Slack, you can also access the QuizKit channel on Slack. You also get help there on a best effort basis. The entire API behind this, behind the IBM Q experience, is all open source. And let's go back to the PowerPoint. Let's just see if we deliver the results here yet. Not yet. Let's go back to the PowerPoint. And look at what that actually means. So with a qubit, I have the possibility to have both a 1 and a 0 and all complex combinations of 1 and 0 at the same time. And that defines something we call a state space. Now, I've got one qubit, that means I have 2 basis states simultaneously. simultaneously. If I have 2 qubits, then I have 4 basis states because both basis states give me 2. Both qubits give me 2 basis states. So for n qubits, I get 2 to the power of n basis states. This is why the power of a quantum computer is doubled every time I add a single qubit, because I add 1 to n. So now I go from 2 to the n state space to 2 to the n plus 1 state space. Currently, the largest machine we have in operation, which is being used for device research and device development, is a 50 qubit machine. So it has, I think that's 1.125 times, more or less, 10 to the 15 basis states. That's quite a lot. The closest number which might have a meaning for you is the number of atoms in and on the Earth. So everything around us, the entire Earth, atmosphere, the sign, everything about the Earth, the number of atoms contained there is about 2 to the 54. So 2 to the 52 to the 54, there was a relationship of 2 to the 4. 2 to the 4 is 16. So the number of basis states in our biggest quantum computer is about something under 10%, 5% of the number, equivalent to 5% of the number of atoms on and in the Earth, just to give you a feeling for it. To model the number of atoms in the observable universe, we'd need a 275 qubit machine, and that's a realistic quantum computer to build at some point, and probably in a not so distant future. We don't know yet, but that just gives you an idea of why a quantum computer is so powerful, in a sense of, if I have a sufficiently large state space, then I can use a quantum computer to solve that. In fact, that is the major challenge with quantum computing, is developing algorithms which take problems which we've traditionally designed to run on classical computers. So these are a series of steps which produce a result. That idea, that trope, that cognitive model of how you program, you need to throw that out of the window with quantum computing. It doesn't work at all. Completely, actually counterproductive to think like that. So you have to translate between the classical world and the quantum world, and it's not trivial. What we can do with quantum computers is we can solve things called hard problems. So if you look at a classical computer, it doesn't matter if it's the Intel 4004 microprocessor, which I first had in my hands. The microprocessor, I think it has something like 12 or 13,000 transistors on it, and that was 1975 or 6. The first real microprocessor. Or if you talk about the IBM P9 processor with billions of transistors on it, they're basically doing the same thing. So they're just executing a series of steps. And the problems you can solve using those classical computers, we call them easy problems, although they're not, but computationally they're easy. Whereas a class of problems which are actually very, very interesting problems, which are hard, so you can't solve them in any scalable, useful way on a classical computer. The most well-known example is the traveling salesman problem, which is to find the shortest distance between a given number of locations, cities. So the idea is that a salesman has to travel between, I don't know, 20, 100 cities. What's the shortest route you can take? And that problem, the size of that problem doubles. Actually, yeah, it doubles every time you increase the number of locations you have to visit. So it's a combinatorial problem, and it's hard. You can't solve it efficiently using a classical computer. I don't know if any of you are addicted to Sudoku. I am. So the smallest Sudoku you can do is a 4x4. Very trivial. The ones you see in the newspaper or in magazines are 9x9. I used to think I was crack at solving Sudoku, so I do the hardest ones in about 3 or 4 minutes. The world record is under a minute. There are also 16 by 16 Sudokus, so I've done a couple of them. It took me about a day on average. There are also 25 by 25 Sudokus. I'm still working on my first one. But as you increase the size of the Sudoku, it becomes computationally completely feasible. In fact, when you get to 81 by 81 Sudokus, it's even using the supercomputer from before would take you forever. So these are also hard problems. Interestingly, there's a subset of the hard problems which are all equivalent to each other, so-called NP-complete problems. What we now know is that a lot of these hard problems are actually easy for a quantum computer. What we also know since October last year is that there are problems which are harder than the hardest problems, which are still easy for a quantum computer. So it's a very, very exciting area, not just for the development of new technology for quantum computing, but also in computer science for developing new algorithms. Where are we using quantum computers? Well, 3 areas basically are under investigation: chemistry, pharmaceuticals, drug discovery, biology, biochemistry. This is an area where it's very close to physics, so the way you describe the problems is very close to describing problems in physics. And this approach or this method we have transferring those problems directly onto the qubits works quite well. In fact, I think it's in December 2017, Nature, there was a couple of articles from IBMers on how to do exactly that. So I recommend you check that out if you want to understand how to use quantum computers in chemistry and pharmaceuticals. Second area is in the area of artificial intelligence. This is a big challenge. It's a big challenge computationally, and it's a big challenge cognitively. How to use quantum computers to speed up machine learning and deep learning. And then the third area is in the area of optimization, so financial analysis, but also network optimization, logistics, planning. So we see these 3 areas. There's an additional area which is the area of cryptography, but I'm going to bracket that out for the moment because it has other aspects and other challenges associated with it. If any of you want to take a screenshot, feel free. For this one, there are some references to papers on arXiv. So these are all free scientific papers on using quantum computers in the finance industry and in machine learning. When we talk about the power of a quantum computer, I mentioned, just add another qubit and you double the power. So some of you are probably thinking, well, why not just get a couple thousand qubits? The reason is that each qubit is not just non-deterministic; it's also error-prone, which means when you manipulate, going back to the circuit where I had the H gate and the observer gate, each of those gates induces an additional error in the qubit. So that means that the qubit can actually be in, although you think it's in a particular configuration, it isn't, it's an error. And the advantage of quantum computing is also the disadvantage with errors, because errors potentiate. So you need to keep the error rate of the individual qubits at as low a level as possible. And in fact, depending on the error rate of the qubits, that basically determines what's the maximum number of useful qubits you can have. And this is where IBM, but also Google, Rigetti, all our competitors, and most people are working on improving quantum computing is by improving the error rates. And IBM has coined the term quantum volume to indicate basically how important these error rates are in estimating and measuring the power of a quantum computer. And I mentioned before the Oak Ridge machine with the 4,608 nodes. With that machine, you can simulate a quantum computer with about somewhere between 46 and 48 qubits. So the interesting observation about that is that that machine cannot even simulate our biggest quantum computer. And if we build even bigger quantum computers with even more qubits, they're no longer simulatable. You can no longer validate and verify that it's actually producing the right result by checking that on a classical computer. It's no longer possible with the largest machines. So we've already leapfrogged classical computing. What we're now waiting for is to combine that leapfrog with applications with the right algorithms to get to quantum advantage. I talked before about the IBM quantum experience, and afterwards we'll go take a look, see if the results have arrived. Obviously, IBM is doing a significant amount of research on quantum computing and building devices. May 2016, we made the quantum experience available. And if we look at basically since 2016 up until about a year ago, the number of people that have used it. In red, you see the people using a quantum simulator we had. I don't know what the blip was. Something happened on that day. And in blue, you see the number of people actually accessing the real quantum computing devices. And so until about March last year, it was around just under 100,000 users. We're now approaching 200,000, and increasingly around about a half the people are actually using the real quantum computers. So a massive uptake. I don't think just the IBM advertising here. I don't think our competitors are quite that far, but I'm sure they're observing a similar growth in the interest and use. What we also offer is a open source API, QuizKit, and QuizKit has different manifestations, different variants. So QuizKit Terra, you can install this. You see the command here. If you've got pip or Anaconda installed, just do pip install QuizKit. It will download everything. It's free. You can get an API key from the login screen I showed you before. It doesn't cost anything. It's all free. Pip install QuizKit, and you can start to write either Quasm code embedded in Python or directly quantum circuits, have them compile and have them run on the back end in the IBM cloud. QuizKit Air is a simulator, so if you're into writing or building or improving the simulators, then QuizKit Air is the thing for you. And QuizKit Aqua, this is the kind of the most interesting part because it's about applications. Now, one of the problems with working at the circuit level using Hadamard transforms and these very basic circuit manipulations of the qubits, it's all very unwieldy and not intuitive and not even remotely obvious how I get from a problem into a bunch of gates. So QuizKit Aqua is basically what we call a transpiler. So it's a translator and compiler, which takes high-level algorithms and spits out a bunch of quantum gates. In some cases, thousands of quantum gates, which you can then run on a quantum computer backend. Basically, it dumps out a bunch of JSON, which describes the gates and the manipulations. All is open source. If you're into compilers, if you're into any kind of device physics, go take a look at the various types of QuizKit. It's real easy to install. There are also a number of tutorials. In fact, if you go on the QuizKit webpage, you'll get a link to tutorials directly. But there's also a community and a very, very active GitHub community. So feel free to get involved in that. I don't know what it's like in your various countries, but certainly within Northern Europe, or actually no, all of Europe, a lot of universities are now offering courses based on using QuizKit. The performance of the various machines, we make that public. So you can see in here the various gate errors. What you don't see here in this screenshot is the temperature. Normally we also show the temperature of the various machines because that has an impact on the error rate. So basically we're very, very public about what's happening with the API and with the machines. So just to recap, we've made the IBM Q network, which is IBM customers who are engaged with us on quantum computing. All the open source software, which I invite you to go and try. And recently at the Consumer Electronics Show in January, we announced the first commercial quantum system, which is the IBM Q System 1. I'll talk about that just at the end. So we have very advanced IBM quantum systems. Some of our competitors do as well. And again, feel free. I encourage you to go and look at what everybody's doing. Rigetti, Xanadu. There's a whole bunch of companies out there working on quantum computing. And I invite you to take active part in the IBM QuizKit community. We launched the QuizKit network in 2016, and our goal, our expectation is that with the IBM Q network, that means with customers who are engaged with us, that we're going to see people reaching quantum advantage in the next 12 to 24 months. There are different models of how people work with us. First and foremost, hubs, but also different types of partnerships, academic partnerships, commercial partnerships, and also members of the IBM Q network. And if we look at the current state of play, I don't know the exact number. Yeah, I think it's 78 members. So industry partners such as Samsung, Daimler, ExxonMobil, a number of hubs, always skips for some reason, a number of hubs. Actually, they're all universities or research organizations. 16 members, so these are also mostly commercial entities. And interestingly, missing from here is DeWitt's. So that's very hot off the press at the University of South Africa. But for you guys, I guess probably the most interesting part is the startups and academic partners. And you know, if you want to learn more or want to get involved over and above accessing the free machines, then contact me directly. You should be able to have, or you should have my email address through the link. So we're very active. We're recruiting partners into the network like there's no tomorrow, and we believe that quantum computing is a very interesting future. So I talked about the IBM Q System 1. There is one of these actually in operation in Yorktown in our research labs. And this is interesting because up to now, quantum computing the focus has been on research and developing technology. And we announced the first machine to actually provide quantum computing I'm hesitant to say as a service, but quantum computing commercially. So it's announced. It's not yet available. And for my IBM colleagues, you will understand the difference. Basically, that means we're going to produce it. We're going to make it available at some point in the not too distant future. But we haven't revealed yet when that will be. but not too long in the future. You'll be able to use quantum computer in a commercial context, and that's interesting because it's implicit in that is that we expect the quantum computers to achieve quantum advantage in the near future. So these are the ways to engage, and if you want further details, then just contact me. So and there's my email address. Just blend it in for a couple of seconds before I go back to. Yeah. I'm sharing two applications, but web browser. Okay. Now let's see what happens here. If anything happens. So we're still waiting. Unfortunately, it sometimes happens. Look at the overview. It's loading. So here I can normally get, yeah, okay. So the reason we're still waiting for the result is the queue at the moment is rather full, but maybe if we have it, I think we now have some time for some questions. So after the questions, we'll go take another look and see if there's something there. So I'm through. I'm finished with my quiz. So I guess I'm open for questions now.
Great. Thank you so much, Dr. Mark.
Chat, or if you want to go on unmute.
Yes, thank you so much, Dr. Mark, for this very valuable and interesting presentation. If anyone has any questions, you can even type your questions on the chat, or you can unmute and ask the question. I see there was a question earlier about, I guess, from Nashat, the difference between IBM quantum computing and IBM mainframe, or IBM quantum computing and also IBM Watson.
Oh, okay. Well, IBM Watson is kind of very nebulous and unspecific because IBM Watson can mean all sorts of different things. Originally, it was the Watson system which was able to hypothesize and thus generate questions to a known answer. Like Jeopardy, when it won Jeopardy. But it was a hypothesis generating machine, basically, which is very useful in machine learning. Since then, Watson has become to mean all sorts of different things. So the comparison is kind of difficult to make. What IBM Q is not is it is not part of IBM Watson. What IBM Q or what quantum computing is not, whether it's IBM Q or anything, any other kind of quantum computing, is big data. So one of the things about the quantum computer is you have a number of qubits, you have a huge state space, and you have to initialize and construct a circuit to manipulate that state space. You have to do all of that within the coherence time. I said at the very beginning, the coherence times, we're talking about 100 microseconds, and the individual gate times are such that within that 100 microseconds, we can do maybe 10,000, maybe 20,000 gate manipulations. So we don't have limitless. If you like, your program is always limited to execute in a specific maximum time. And in that time, you have to initialize the state space in some way, and you have to do that all individually. So no big data. In fact, one of the most interesting approaches to developing algorithms for quantum computers is to take classical algorithms and cut them up in such a way that you find a particular slice in your classical algorithm which is not data intensive, but is compute intensive. If you can do that, then you can think about offloading that particular part onto the quantum computer. So there is an algorithm called the variational quantum eigensolver, which initially was used to solve the binding energy calculations for chemical compounds. In my presentation, I put up a screenshot of some scientific papers. I think one of them was the paper on using the variational quantum eigensolver in the finance industry. A few weeks ago, I was at a conference. Somebody's using the variational quantum eigensolver to factor large numbers even faster than Peter Shor's algorithm. So a lot of the work in quantum computing is, we have a set of tools which we have available, which we know work. How can we apply those tools to different application areas? I don't know whether that really answered your question, but it was a kind of rambling, unspecific answer, but I hope I helped you. So is there an easy example from classical computing that could be translated to quantum improvement computing? I don't know if you were here at the start of my talk, but I talked about the Peter Shor's algorithm. If you want to factor a large number, let's say you have a 1024-bit number, and you know it's not prime, and you want to find out its prime factor. Now that is a computationally very difficult problem. If you use the best known algorithm we have to date on the biggest supercomputer we have on the planet, then factoring that 1024-bit number would take you around 17 billion years, so longer than the universe has been around. Peter Shor in 1994 came up with an algorithm which, if you did the same, we need about 10 minutes. So 17 billion years to 10 minutes. That's the power of quantum computing. Don't worry, and I also said this at the beginning, factoring a large number is the core of public key cryptography. But don't worry, because Peter Shor's algorithm will need probably hundreds of millions of qubits. Right now we have somewhere between 50 and 100 qubits. So we're a very, very long way away from having that number of qubits. And his algorithm would need a coherence time measured in minutes or hours. Currently, we have a coherence time around 100 microseconds. So I don't see a problem with public key cryptography anytime soon. But what I do see is a way to fundamentally, exponentially speed up a particular algorithm. And in fact, that's all the algorithm research going on in quantum computing. It's always about finding that exponential, or we actually call it super polynomial speed up, making a problem execute in a completely different area of performance. So let's see, what are the questions? Quantum computing and IBM mainframe, yeah. Probably where we are at the moment, we have machines which are being used for research at IBM and for IBM and for customers. The machines are all physically located in IBM research locations, and that won't change. We announced the IBM Q System 1, which will also be located in an IBM location and available via the clouds on a commercial basis. The research machines are also available via the cloud. So that physical location in a physical IBM compute center, that won't change anytime soon. I'm sure at some point in the mid-term future, you will start to see people have quantum computers in their own compute center. Given that the things operate pretty close to absolute zero and under ultra-high vacuum, you do need some special skills to make that work. It's not rocket science, but it's not trivial. Ultra-low temperature physics or ultra-low temperature environments and ultra-high vacuum environments. It's not impossible, but it's not trivial. What you're almost certainly going to see is quantum computers being used in combination with either mainframes or supercomputers as a type of accelerator. So your question about mainframe, yes, probably. So let's see, what are the questions? Watson, we did.
Dr. Mark, maybe do you have some
Yes.
Overview on the latest announcement that IBM made on June 12 in terms of expanding its quantum computing program to Africa with the WITS University in South Africa?
Yes, so I mentioned that the WITS is now a hub. We will be running, and it's not confirmed, but as far as I know, it's not confirmed. But we will be running a workshop for universities, developers in Johannesburg. I think either the end of this year. I think it's provisionally the end of this year, but no promises. It might be the start of next year. And that will be a kind of launch kickoff. And I know that there is also some discussions going on with and between the WITS and other universities and other countries in Africa. And my own personal connection, as a young boy, I spent a lot of time in Uganda, so I love East Africa. Just call me.
All right, that's great.
So Africa has a lot of potential. Yeah, we see a lot of potential, a lot of very, very good people.
Excellent. There's one more question from Raji. What's the difference between quantum computing and infrastructure as a service, cloud computing?
Okay. Well, I mean, in a certain sense, when you access the IBM quantum computers, the ones we see here, I don't know if you're still seeing them. These machines on the right, the three freely available quantum computers on the simulator. Then you're accessing them via, or it used to be called IBM Bluemix. I think it's now called IBM Cloud, which is, among other things, infrastructure as a service. So typically, in the future, you're going to be using some kind of infrastructure as a service connector to talk to the quantum computer. So that's the only overlap that I can see at the moment.
Great. Thank you so much, Dr. Mark. I think we were about 10 minutes over time. This was a very good, very useful presentation. Thank you so much. And thanks for everyone who attended this webinar. The recording of this webinar will be available on the link that Warud just pasted in the chat. And if there are any additional questions, I guess Dr. Mark, can they contact you directly through your email address? Is that okay?
Sure.
Okay.
I made it a bit slower in reacting, depends on how many emails I get, but yes.
Sure, we understand, yes. Thank you so much for your time, Dr. Mark, and thanks for everyone for attending.